In the previous video, we talked about benzene and we called it an aromatic compound. There's lots of other kinds of aromatic compounds. So in this video, we're going to define aromaticity, what makes something aromatic. And then we'll talk about variations of that, namely what makes something anti-aromatic and what makes something non-aromatic. Okay. So in the last video, right, we said benzene is aromatic. So just to refresh our memories here, benzene is a ring and it contains conjugated double bonds. So one might think, right, that if you have a ring that contains conjugated double bonds, maybe that's aromatic, right? Well, that's actually not the case because we said that one thing that makes benzene unique is that it's extremely stable and that its double bonds are very unreactive. So let's say we take 4 double bonds and we put them in a ring. That's called cyclooctatetraene, right? We have cyclooctatetraene here. If we react that with bromine, it rapidly undergoes a bromination reaction. So apparently cyclooctatetraene is not aromatic because it doesn't have the stability that benzene does. It's reactive, like its double bonds react as if they were isolated double bonds. What if we have one less? Instead of having 3 double bonds, what if we had 2 double bonds in a ring? That's cyclobutadiene. Cyclobutadiene is extremely reactive and it undergoes rapid dimerization to this molecule, which eventually becomes cyclooctatetraene at very low temperatures. So this thing is extremely unstable. So it's obviously also not aromatic. So that's weird. What is so special about 3 double bonds that makes this compound aromatic? Well, let's look at molecular orbital theory to get some insight into this. Right. So first let's talk about cyclobutadiene. Cyclobutadiene, it turns out, is called anti-aromatic. We said it's extremely reactive and it's almost impossible to isolate. Cyclobutadiene is anti-aromatic and it's strongly destabilized, unlike benzene, which is strongly stabilized. Let's talk about why. If you think about the bonding in cyclobutadiene, right, there's 4 p orbitals that are in a ring and they're all overlapping each other. Just like in benzene, there's 6 p orbitals that are overlapping, right? So we can use molecular orbital theory to build a molecular orbital diagram of this, right? And if you have 4 p orbitals, you're going to have 4 molecular orbitals that we can analyze. So if you look at those 4 molecular orbitals, right, this would be the line between bonding and anti-bonding. This is called non-bonding, and actually I drew my line kind of poorly. These, you have 4 electrons from cyclobutadiene, right? We can have all 4 of those p orbitals in phase with one another. And that's going to be a bonding interaction, right? And we're going to put 2 electrons in that orbital. But you can have 2 non-bonding orbitals that I'll draw in the next slide, and each one of those gets a single electron. Remember that you don't pair electrons until each orbital gets 1 if they're equal in energy. So we have 2 unpaired electrons. And having unpaired electrons makes things extremely reactive. So according to molecular orbital theory, unlike benzene, which all of its orbitals were full, all of its bonding orbitals were full, in cyclobutadiene, we have 2 non-bonding molecular orbitals that each have an unpaired electron, which is very unstable. Okay, so just to get a clearer picture of what's going on here, because I think this is interesting, right? If you think about cyclobutadiene, each carbon has a p orbital on it, right? And according to molecular orbital theory, the most stable configuration of those 4 p orbitals is that they're all in phase with one another. So we will depict phase by shading 1/2 of the p orbital. So if all these lobes of the p orbitals are in phase, then that's going to be the most stable, and that gets 2 electrons. Then we said this line is between bonding and non-bonding, bonding and anti-bonding, right? And as we go up in energy, we always add a node. So we can have a node, this way between two carbons, and I'll draw that over here. So now, when you go through a node, remember you change phase. So these two would be out of phase with one another, and these two would be out of phase with one another. So we have a bond here, but we have an antibond, and then we have a bond here, and we have an antibond. So each bond is being canceled out by an antibond, and that's why it has non-bonding character, and we put one electron there. But we can also bisect the molecule through these two p orbitals. So the way we can draw this is that if you have a node going through an orbital, there's no electron density. You always change sign at a node, so you have two isolated p orbitals. They're not bonding with each other, so we have an electron there. So we have one electron in each one of these non-bonding orbitals. And then we could have two nodes, which would look something like this, where now every p orbital is out of phase with every other p orbital. So this, we change phase every time we go through a node. So now there's no electrons here, but this would be an antibonding orbital because these are out of phase, these are out of phase, these are out of phase, these are out of phase. Okay, so what about cyclooctatetraene? Well, we have 8 p orbitals. We need 8 molecular orbitals. I'm not going to draw them, but they're on the next slide. Cyclooctatetraene is actually non-aromatic, unlike cyclobutadiene, which was anti-aromatic. We'll talk about why in a second. Okay, so if cyclooctatetraene was flat, this is what it would look like. You would still have 8 1, 2, 3, 4, 5, 6, 7, 8 molecular orbitals. You'd still have 2 unpaired electrons. So based on this molecular orbital energy diagram, you would expect cyclooctatetraene to also be anti-aromatic, right? But that's only if it's flat, right? If it's not flat, then we don't have all 8 orbitals interacting with one another. We might have some interacting with each other and some not. And that's what happens. Cyclooctatetraene can actually distort itself. So instead of having 8 overlapping p orbitals, we have 2 p orbitals overlapping here to give a pi bond, and 2 overlapping orbitals here to give a pi bond, and 2 overlapping orbitals here to give a pi bond, and 2 overlapping orbitals here to give a pi bond. So it acts like 4 isolated pi bonds as opposed to one big molecular orbital. Why would that be? Well, because if it does this, it actually doesn't get destabilized. So if a molecule has an opportunity to distort from planarity, it will, because if it was planar, it would be destabilized and it would be higher in energy, so it moves in order to avoid that destabilization. Okay, so can we generalize this? Yes. It's called Huckel's rule, after this cat that is in various children's stories, or maybe this dead German guy. So Huckel's rule says to be aromatic, you have to have a ring, and you have to have 4n plus 2 pi electrons, right? So if n is equal to 0, that would be 2 pi electrons. If n is equal to 1, we'd have 6. If n is equal to 2, we'd have 4 times 2, which is 8, plus 2, which is 10. Then 14, then 18, then 22, then 26, etc. So if you don't have one of these numbers of pi electrons, then you're not aromatic. This one has 4, so that's not going to be aromatic. It falls in between 2 and 6. This one has 6, so it is aromatic. This one has 2, 4, 6, 8 pi electrons. It's not aromatic. If we had 10, then we would be aromatic. So one thing that you must have in order to be aromatic is Huckel's number of pi electrons. Okay, what else do you need to be aromatic? Well, we just said in order to be aromatic, those orbitals need to talk to each other, so you have to be flat. You have to be in a ring. And so in order to be aromatic, what you need is to be in a ring. All the carbons need to be sp2 hybridized. This guy is not aromatic because this carbon is not sp2. You have to be planar, so this guy is not planar. You have to have 4n plus 2 pi electrons. So what happens if you're anti-aromatic? Well, you need to be in a ring, you need to be all sp2, and you need to be planar. So this is pretty much cyclobutadiene. Since it's in a 4-membered ring, it can't distort from planarity like cyclooctatetraene is. It has 4n pi electrons, so that makes it anti-aromatic, whereas if you're non-aromatic, you're either missing a ring, you're missing all sp2, so this would be non-aromatic, or you're not planar, so that's why this one is non-aromatic. Okay, so what about annulenes? We said 10 is a magic number, so this guy is actually aromatic. What if you had 14? This one is also aromatic, because these guys can be planar if they want to be, which gives them some stabilization. Okay, to summarize, what makes something aromatic? You have to be in a ring. You have to be all sp2. You have to be planar. And you have to have 4n plus 2 pi electrons. If you satisfy all those criteria, that gives you an added degree of stability, which makes you very happy if you're a molecule. If you only fail in Huckel's rule, like the best example of an anti-aromatic compound is cyclobutadiene, now you're anti-aromatic. If you fail in any other rule, you're going to be non-aromatic. And in the next video, we'll start talking about aromatic heterocycles.